So today we shall determine the inverse of a matrix with the help of elementary row operations, and after that we'll start our new topic, that is vector spaces. Okay, so finding inverse of a matrix using elementary row operations. Okay, so of course we'll start with the help of an example, and the whole idea will be that let's start with an example, because most of you have already done, I suppose. So let's assume that we have this example. And we want to find out the inverse of this. So we always start with the matrix this, right? So identity of the same order, right? And then we implement row operation in such a way that our A should replace by an identity matrix. And the other side, whatever the matrix we'll get, that will be nothing but the inverse of the given matrix. Okay. So this is there, and we shall have the identity matrix over here in this way. Okay, now we want to make identity over here, so that means we need zeros over here first of all, and we have leading entry 1 over here. Okay, so how are we gonna get the zeros? Of course, we'll implement operations, row operation on R2 and on R3. So that's how we can get this one. So let me make some space over here. Minus energy. Take. Is it fine? So now this will be 1 1 0 1 0 0. So first row will be as it is, and if we subtract R1 from R2, so this will be 0 1 and minus 1 minus 2, 0 will be subtracted, right? So that will be what? 1 over here. Similarly, if you subtract, therefore it becomes minus 1 over here, and it becomes 1 over here, it becomes 0. And if you apply row operation on R3, you'll get 0 over here, minus 2 2, and this is minus 1, and this is 0, and this is 1. Yes, are you with me on this?
Yes, sir.
Okay, so I'll paste this thing over here just for the reference, right? So now if you see this, you've already 0 over here, and your aim is to make the identity. Okay, so here we need to come up with the fractions. So now you want 1 over here, so there is no other choice. You have to divide the R2 by 2, and similarly you too want 1 over here. So that 1 in the next stage will become 0, right? After implementing the proper row operation. So now, first of all, if you want to make 1 over here, so what do you need to do? You simply operate on R2 minus half times the R2 and R3 minus half times the R3. That's how it works. So this will become what? Of course, the first row will still remain as it is, and the second row will get divided by minus half. So here you get minus half, here you get half, minus half, and 0, right? Yes. So again, in the third row also, you'll divide by minus half. So this will be something like this. Yes. Is it fine? बात सही है?
Yes, sir.
ठीक है. So see this. Now, so your next step would be you make 0 over here. Okay? You make 0 over here. So for this, what should we do? Yes. And 0 over here, 0 over here as well. बोलो क्या करें यहाँ पे 0 बनाने के लिए yes simply you operate on R3 minus R2 so you are left with of course your first two rows will be same and your third row will look like 0 0 minus half minus 1 plus half so that is minus half half minus half 0 here you'll get plus half here it will still remain minus half. Yes, are you with me on this? So now
Yes, sir.
we know that we are in the process to make the identity matrix on the left hand side. So here you need 1. So now in order to make 1 over here, you simply replace R3 by minus 2 times the R3. Okay, so you will reach again the first two row will remain same and the third row will be something like 1 0 minus half and 1. Yes, is it fine?
Yes, sir.
So what we need now, again, we are in the process to make the identity. So we need 0 over here, okay? And we need 0 over here. At these two places, we need 0. So first of all, let's make it very simple that make 0 over here. So for this, you simply replace your R1 by R1 minus R2. That's one thing you can do, okay? Or you can replace or you can make 0 over here. That will be better because if you first make 0 over here, then it will not disturb this entry, right? So for making 0 over here, what should we do? You already have this 0 0 1. This 0 will not disturb this entry. So you simply replace, you simply multiply this row. That means you simply multiply R3 by half and add it to the R2. Then of course we'll get 0 over here. So that after when we operate on R1, so it will not make a non-zero entry over here. It will not disturb this entry. So first of all, operate on R2 plus half times the R3. So here you will get what? 1 1 0 1 0 0 and now you add, so this will remain same. Why? Because these two entries are 0 and if you multiply this by half and add it to there, so that will become what? 0. Multiply this by half and add it over here, again half. This by half, add it over here, so this will become minus 1. And this by half and add it over here, so this will become half. And R3 will remain same. Yes, are you with me on this?
Yes, sir.
Yes, sir.
Okay. Now, what I'm trying to say is, now if you see that we are slowly reaching towards the identity matrix on the right hand side. So now only one component, this one, needs to be 0, otherwise everything has been fixed. Okay, so everything is in apple pie order. So only this entry should be replaced. So for this, what should we do? We simply operate on R1 R1 minus the R2. So 1, 0, 0. So here 1 minus half, that will be half. And here 0 minus minus 1 plus 1. And here, so that will be 0 minus half minus half. Yes, fine. The rest of the entries will remain as it is. There will be no change in those entries. So now this is something which should be equal to identity on your left hand side of this matrix and A inverse on the right hand side. So this entry will give us A inverse. So that means our A inverse is nothing but half 1 minus half, half minus 1 half, 0 minus 1 1.
Yes, sir.
Is it easy? Okay. So now come to our next part. So we shall start with the idea of vector spaces. So before going to the formal definition of vector spaces, first of all, you know the word vector, but you know this word in terms of physics only, not in terms of mathematics, right? Most of the time you deal with the vectors in a physical sense. What is vector? Yes, a quantity
which has both magnitude and direction.
having
Magnitude
yes,
and direction.
having magnitude and direction. Yes, fine. This is something which we do in physics, right? But there are other characteristics of the vectors. For instance, vectors have nice property. And what is that nice property? That they preserve the addition and scalar multiplication. What does that mean? The point I want to make is, if you have a vector, let's say u and v, and if you add them, so their addition will also be a vector, right? If u and v are vectors, then u plus v is what? A vector, right? And if you make it alpha times u is again what? A vector. Not every operation can be preserved. Why? Because if you take the dot product of that, then that is what? Not a vector, right? Are you getting my point?
Yes.
So if you're adding two vectors, you're getting another vector. If you're having a scalar multiplication of vectors, you'll get a vector in the result. But if you're taking the dot product of two vectors, it will not result in a vector. So vectors preserve these two operations, that is addition and the scalar multiplication. So we shall take this idea to the planet mathematics and try to decipher it algebraically. We shall translate this idea in mathematics. So in mathematics, we will be looking for the sets which will be satisfying few properties. On the basis of those properties, we'll say that whether a set forms a vector space or not. Now, magnitude and direction will no longer be the point of focus. We'll be more concerned about the algebraic properties that will be possessed by the vector space. And we shall talk about those properties in the detailed definition of the vector space. So let's see. So consider a non-empty set V. Whenever U and V belongs to V, then U plus V should belong to V, and for K belongs to real, and it may not belong to real every time, but we are not going to discuss that. Or at this point of time, K is a real number. That's what you assume. And if your K belongs to the real number, for any K belongs to R, K times U also belongs to V, then V is called a vector space. Over R if it satisfies the following properties. If it satisfies the following properties. And the first property, I'll call it as A1. So A1 is whenever your U, V, W, three vectors or three elements belongs to V, then it should satisfy this. And this is something which we call it as associative property. And the next one is there must be a zero vector in V. There must be a zero vector. Zero must belong to V such that if you add this zero to any element of U, it will not make any difference. It will still remain U. For every U, if you add zero vector to it, it becomes U always. Okay. So now your A3. For every U belongs to V, there must exist minus U belongs to V, such that whenever you add U and minus U, it will always be a zero vector. That zero vector which we have discussed over here, this zero vector. Okay, so if you add U and minus U, the same zero vector will appear as a result. And fourth property based on addition. That's why I'm stating it as A property, meaning based on addition. So for every U V belongs to V, U plus V should be equal to V plus U. This is something which we call it as commutativity. Now, this is something which may be kind of strange to you. You feel like that it doesn't matter if you add U and V and U and V and U, they are the same. But it doesn't happen every time. So that we'll do in terms of example that we need to understand. Okay, because that addition doesn't mean the usual addition, and the multiplication doesn't mean the usual multiplication. We can change the addition and the multiplication in a generalized way. So these are the addition properties, and there are four multiplication properties as well. So we call it as, so first one is M1, that is what? For any alpha belongs to R, that means real number, and your U and V belongs to the vector V set V, U plus V will be alpha U plus alpha V, right? It should hold. Okay, every time. And there is another property M2, and that's what? For any alpha beta belongs to the R and any U belongs to the V, And if you take alpha plus beta times the u, it should be equal to alpha u plus beta u. And similarly, there is third property based on the scalar multiplication. That is, if you have for any alpha beta belongs to the R and any u belongs to the V, then alpha beta times u should be equal to alpha times beta u. And the last property, and that is there must exist a unit vector for unit scalar, for unit scalar, there must exist a 1 belongs to the R, right? Then 1 times the u should be equal to u for all u belongs to the V. Yes, you all with me? Okay. We'll understand with the help of examples. Okay. So this is something which we call it as, if V satisfies all those 8 properties, then we say that V is a vector space over R, right? And in general, we may have we call it as vector space over a field F, but that field concept is right now it's not in our syllabus. Okay, so I'm not going to the field. We'll be very specific. It should be either over R or over C. Okay, so in general, V is a vector space over a field F, but in place of F we'll have either R or set of complex C. All right, let's start with a very simple example, and that's what show that R2, and R2 is nothing but R cross R, okay, is a vector space over R, right? So before going to prove these 8 properties, first of all, understand what is R2. Let's say you have A, that is 1, 2, 3, and you have B, let's say 1, 4, 5. So how do you calculate A cross B? Yes, tell me.
1,
Yes, they are tuples. What are they? They are tuples. 1, 1, 1, 4, 1, 5, 2, 1, 2, 4, 2, 5, 3, 1, 3, 4, 3, 5. So how do they look? Can you tell me how did they look? On the real line, let's say it is 1, it is 1. So that will be 1, 1. It is 1 and it is 2 and 1. So this point will be 2, 1. So they are what?
set of points.
Points हुए ना? 2D points हुए कि नहीं? And think that you have replaced your A by R and you have replaced your B by R. I mean, now how this set will look like? Extend this idea, A cross B to R cross R, and tell me.
For XY plane.
Yes, it's nothing but whole XY plane, right? So now given that this is our V set, R cross R, and scalar will be from, so there will be 2 sets sort of, right? Scalar set is R. So what we need to prove? We need to prove that V is a vector space over R. This is your V, this is your R. First of all, you need to prove that this thing, whenever your U and V should belong to V, your U plus V should belong to V. That's what you want to prove. So think this V as a whole bag. Okay, this R cross R is a bag, right? So this bag should be closed under addition. So what does that mean? If you pick two elements from this bag, right? If you pick two elements of this bag, and if you add those elements together, the resulting element should also lie in the same bag, right? जैसे सोचो R में देखो, R में अगर तुम्हारे पास 5 और 2 हो, 5 और 2 को ऐड किया, you take two elements from R, you have 5 and 2, and you add them together, 5 and 2, and 7 will be again a real number or not?
Yes, sir.
Yes, sir.
Yes, sir.
Now tell me, if you take a set of natural number, you have two natural number, you add them together. Let's say one is 10, another is 11. You add them together, what do you get? 21? Yes?
Yes, sir.
Yes.
So that 21 means what? That 21 is again a natural number. But this
Yes.
may not happen for the every operation. Let's say take an example, you take subtraction. You have one element 7, you have another element 10, you subtract 7 minus 10. So the resulting number will be minus 3, which will not be a natural number, right? Which
Yes.
does not belong to that bag. Okay. So first of all, the very first operation is what? As I've marked over here, that first of all, the bag should be closed under addition, right? That's what we have said. So now, before saying that bag should be closed under addition, you must be able to recognize its element, that how these elements look like, that how these two elements will look like. So if you're picking two elements, U and V, from our given V, and that V is nothing but R cross R. So how the element of R cross R will look like? Tell me.
X1, Y1, X2, Y2.
Yes, इसी टाइप में लिखेंगे तो U कैसा होगा? So let's say your U will look like U1, U2, and V will look like V1, V2. And U1, U2 both are real, and V1, V2 both are real. Now, if you add U plus V, so that means you are adding U1, U2 and V1, V2. And how you add these two elements? How you add these elements? You simply add them coordinate wise. Okay? You simply add them coordinate wise. So that means this will look like U1 plus V1, U2 plus V2. Now, what can you say about this element? Will this element also belong to the bag?
Yes, sir.
Why is it so?
So because we have constrained U plus V belongs to V.
Yes, so addition of two real is also real, right? So that makes sure that since your U1 and U2, U1, U2, V1, V2 belongs to the real, that's why your U1 plus V1 and U2 plus V2 will also belong to the real. So that means your U plus V should belong to what?
V.
V. Plane में गया ना? ठीक है?
Yes.
So ultimately what happens, you have taken two elements from the coordinate plane, right? This UV, and you added them together, and in result you have also produced an element, you have also obtained an element which belongs to the coordinate plane. So that means U plus V belongs to the capital V. So which actually indicates that your V is closed under addition. Is it true? Now the second part. We will be proving those 8 properties in our upcoming lecture. So I'll prove just one more property and then we shall stop over here. So if you look at this, now the second part is if your K belongs to the R, then your KU should also belong to the V. Okay. So let's implement this idea into that. So that is, you have already U. Now you take any K belongs to the R. Now, if you consider KU, so that means K times, what is U? U is nothing but two tuple, U1 and U2. So this becomes your KU1 and KU2. Okay.
Yes.
So अब ये कहाँ जाएगा? Yes.
So we can check.
Closing the
V के अंदर है ना? So
Yes.
again, therefore KU should also belong to the V. So therefore V is closed under what?
Multiplication.
Yes, scalar multiplication. So we'll be proving the 8 properties and we'll show in our upcoming lecture that this is going to be a vector space.